And thank you to John, our expert photographer here. He's also with the Acton Wakefield Watershed Alliance.
Multitasking. That's it.
All right, that's it.
Excuse me, is there an access code for Wi-Fi?
Yes.
I'll come help you with that.
I believe it's MILL, capital M-I-L-L, and then 2020. See if that works.
Is this thing isn't?
Yes, that should work.
It's not.
It's not.
It's not.
It's not working.
Oh wait, is there a? Oh, it's. Let's see. Let's see. Oh, there we go.
You got
Now
it.
we're working.
All right.
You have to turn it on.
Minor details.
All right, can everyone hear me okay?
No.
No? How about,
Do what you need to do.
okay. How about now? No? Now? Okay, excellent. All right. Oops. Now I'm going too far ahead. All right, well, thank you all. Thank you for the introduction and to you all for being here. This is my first presentation in person in probably almost 3 years, so this is exciting to be here. To get us started today, I'm going to give you a preview of the key findings from the soon-to-be-released state climate assessment. This project was funded by the New Hampshire Department of Environmental Services and completed by myself and my UNH colleagues, Drs. Cameron Wake and Elizabeth Burakowski, both from the Earth Ocean Space Institute. Today's presentation is going to focus on statewide changes, but the report will include local scale information on past and projected climate change at select New Hampshire cities. So this is going to be a little bit much for first thing in the morning, so hang on, all right? So to start us off with a bit of background, New Hampshire itself is located within the northeast climate region, where the distinct seasonality supports a diverse natural landscape adapted to the extremes of cold, snowy winters, as well as warm to hot and humid summers. New Hampshire's proximity to the coast and location below the confluence of 3 major storm tracks result in a humid climate and relatively uniform precipitation distribution, averaging about 43 inches annually. However, local temperature and precipitation values can vary from the state averages due to distance north as well as inland and elevation. So at daily scales, New Hampshire's weather is highly variable and capable of producing severe conditions, including extremes in both warm and cold temperature, as well as precipitation resulting in floods, as well as droughts. So since the beginning of the 20th century, New Hampshire and New England as a whole has become warmer and wetter, with an increased occurrence of both warm and wet weather extremes, which is kind of a theme you're going to hear over the next few minutes here. And so as the dynamics of a changing global climate system continue to impact New Hampshire, the characteristic climate of the state will inevitably change. All right, so starting with the past. So to assess past changes in New Hampshire's climate, trends in state average temperature and precipitation were evaluated along with local scale trends and variability in daily meteorological data. So the trends in average statewide temperature and precip since 1901 were quantified using data from NOAA's U.S. Climate Divisional Database. And then local scale variability of trends in both average as well as some extremes in temperature and precipitation were quantified using daily meteorological data from 10 of the state's global historical climatological network stations. And so just as an example, some measures of extremes would include things like number of days exceeding a certain threshold, so like days with precipitation above 1 inch, or days with temperatures above 90 or 95 degrees Fahrenheit, things like that. And so we calculated trends in 32 different sort of daily or local scale variables for the 1971 to 2020 time period. So that was at all 10 stations. And then we used some of the long-term records at Durham, Hanover, Keene, and Berlin to look at the full 20th century climate change. And so the following slides are going to highlight some of the most important changes observed to date. And all of these trends, just for reference, were calculated and tested for significance. And these significant values are you'll see are going to be highlighted in bold and underlined. All right, so starting with some of our key findings. Compared to the rest of the U.S., generally speaking, the Northeast region is one of the fastest warming regions here in the U.S. And seasonal temperature differences are decreasing in response to winter warming rates that are 3 times faster than summer. So it's really our winter season that's doing most of the warming here. And climate change in New Hampshire is following this larger regional trend. So with an average increase in temperature of about 3 degrees Fahrenheit since 1901. And again, the highest warming rates that are seasonally were observed in both fall and winter. So the cold season is warming faster than the warm season. And then as winters warm, there is a decrease in the frequency and severity of cold extremes and an increase in the number of thaw events, both in the season and at the tail ends. And so, these increasingly milder winters have led to a decrease in snow cover and an earlier snow melt, as well as spring ice out dates are leading to an overall shorter cold season. So like temperature then, total annual precipitation also increased since 1901, and it's largely due to increases in heavy precipitation, most of which has been occurring since 1971. The number of multi-day events, so these big storm events exceeding 4 inches, increased for seacoast stations, while areas inland and north, so this region here, saw an increase in the number of daily events that exceed 1 inch of precipitation. All right, so as the average annual temperature increase, so we're going to start off with temperature, the warming rate was not evenly distributed seasonally or even daily. All right, so the graphs here represent the continuous record of state averaged mean annual maximum on the left and minimum here on the right temperature over the past 120 years. So we started everything at 1901. So obviously there's considerable year-to-year variability, but significant trends occurred in, both over the 20th century as well as over the past 50 years. Overall, there was significant warming trend in state average mean annual maximum temperature of about 2 degrees Fahrenheit during the 20th century, and then a near doubling of that rate occurred over the past 50 years since 1971. Along with that, we saw a significant increase in mean maximum temperature in all seasons, so breaking that up into the seasons. We also saw increases, and of course the greatest warming rate occurred during winter. So while the days warmed, the rate of warming was actually greater for minimum temperatures. So nighttime temperatures warmed at a faster rate than the daytime temperatures, at a rate of about 3.5 degrees Fahrenheit since 1901. And again, most of that warming occurred since 1971. Again, significant increases in seasonally averaged minimum temperatures occurred, with the greatest warming again in the cold season. And so overall, mean annual temperatures across New Hampshire increased at a faster rate over the past 50 years. So warming over the past century, but a lot of that is accelerated over the past 50 years. All right, so since most of the action's happening in winter, let's take a look at winter warming. And so again, while warming occurred across all seasons, the greatest seasonal warming rate occurred in the winter season, with winter nights warming at a rate of over 1 degree Fahrenheit per decade since 1971. So 1 degree Fahrenheit each each decade since the 1970s. And so as our winters warm, we've seen a decrease in the frequency and severity of cold extremes, along with an increase in the number of thaw events. And so looking at kind of more details at the weather, the 10 weather stations, all 10 showed an increase of anywhere from 6 to 14 degrees Fahrenheit in the coldest night of the year. So our coldest nights are warming. And then at 9 of the stations recorded showed a decrease in the number of days with minimum temperatures below 32 Fahrenheit as well as 0 Fahrenheit. So again, these very cold thresholds are warming. And then as a result of this winter warming, there was about a 10% decrease in what are called heating degree days, which indicates a reduction in energy required for indoor heating. So those heating degree days are kind of a measure that electric companies use to determine how much energy is needed to heat a home during the winter season. And so, reduction in heating needs might sound like a good thing. The warming that's happening over the summer has caused a similar increase in the amount of energy required for cooling, so the two are going to offset, possibly have more cooling needs in the summer to come. So, in addition to fewer cold extremes, these milder winters are associated with more days above freezing and therefore less snow on the ground. So for several decades, New Hampshire DES has maintained a set of snow sampling sites across the state to better quantify the amount of water stored in the seasonal snowpack, which is called snow water equivalent, or SWE. 3 of the 5 sampling sites in the Lake Winnipesaukee watershed, along with the Owlbrook sampling site in the Squam Lake watershed, all indicate significant declines in annual maximum snow water equivalent, or the amount of water in the snowpack. And this ranks consistent with 28 other long-term ice out records from New Hampshire, Maine, and Massachusetts that we evaluated. And along with temperature, precipitation measurements are commonly used indicators, and across New Hampshire, total annual precipitation increased as much as 19% since the start of the 20th century. So this is that wetter piece. So the climate, or the graph that we have right here, shows the continuous measure of total annual precipitation averaged across the state since the beginning of the 20th century. Again, year-to-year variability is here, but again, another significant increase in total annual precipitation was observed. Seasonally, though, the largest increases in precipitation again occurred in winter, with more modest increases during the fall and summer seasons. But the real story with precipitation is the amount, or the increase in precipitation that can be attributed to an increase in the amount of rain falling, or the intensity of individual precipitation events, either at the daily time scale or with the kind of the multi-day big storm systems that we get, all of which have increased regionally over the past 50 years. So for example, there was an increase in the number of daily, so 24-hour precipitation events per year exceeding 1 inch across inland and northern parts of the state. And then, of course, near the coast, the number of sort of multi-day storm systems exceeding 4 inches of precipitation increased along the seacoast, as well as at some locations in the White Mountains. And so overall, the combination of above average precipitation amounts and more frequent extreme precipitation events has increased the risk of flooding across the state. So that's a summary of kind of where we are now. And so looking ahead, regions like New England that have kind of warmer offshore ocean currents, which we have to our south, these areas can expect to see increases in the total amount and intensity of precipitation as temperatures rise. The two patterns are connected. And so the resulting changes in regional hydrology have the potential to impact water availability and quality, while milder winters will be associated with a decrease in snow cover, a shift toward more precipitation falling as rain instead of snow, and likely result in a shorter cold season and longer growing season potentially. All right, so to assess future change, we have to look to models. And global climate system models are used here to simulate Earth's potential future climate by projecting today's climate conditions decades into the future for different socioeconomic scenarios, or what we call pathways, leading to either lower or higher atmospheric greenhouse gas concentrations. All right, you may have heard of these as emissions scenarios. They're more, just again, pathways to greenhouse gas concentrations that lead to a certain amount of higher temperatures. All right, and so the following figures are set up to show both the observed and projected future temperature and precipitation to illustrate kind of the full extent of modern era climate change here in New Hampshire. And so in this example, we see state averaged annual mean minimum temperature, where the thick black line shows historical observations from NOAA's U.S. climate database, and the overlapping thin gray line, or overlapping thin line, shows the model simulated values, which include historical estimates that were modeled for the period of 1980 to 2005, and those are shown in gray, and then the projected values go from 2006 to 2099. So now each climate model projection represents only one possible outcome for the given variable. So we used a climate model ensemble, which is a group of climate models to capture the range of future climate projections that result from each, or how each model simulates Earth system processes. So this is kind of the pattern that we're going to be looking at for the figures coming up here. And so here we have the future projections for the full ensemble are shown in blue for the low concentration pathway. So this is assuming that as a society we do take some measures to mitigate greenhouse gas emissions. And then the red indicates, or the red represents a higher concentration pathway that assumes, it's what we used to call the business as usual scenario, but it assumes that we don't actively try to mitigate. Any mitigation just comes from improvement in technologies and efficiencies. All right, so the key findings here show that temperatures across New Hampshire, as expected, will continue to rise through the 21st century. So continued rising temperatures, but how much warmer we get depends considerably on the amount of global atmospheric greenhouse gas concentrations there are, and any actions we take over the next few decades to significantly reduce our emissions and resulting concentrations later on in the century. And so, just like what we saw in the past, as our climate warms, the warmest daily temperatures are going to increase, which is going to increase the frequency of hot temperature extremes. Then in winter, as they warm, the severity of cold extremes is going to decrease along with snowfall and snow cover. And then for precipitation, right, that's expected to increase. And again, a lot of these increases are going to be due to increases in precipitation extremes. What's interesting with precipitation is that seasonally, we expect to see more increases during fall and winter, and only modest increases, or really not much change in the summer months. And that sets the stage for, as we get wetter, we might have a more or a greater occurrence of short-term drought during the warm season, because without a change in precipitation during the summer season, any changes in precip won't offset the expected warming to happen. So we're going to have more evaporation, leading potentially to drier summers while everything else gets wetter. All right, so all right, let's kind of go through temperature here. So focusing here on the maximum temperatures, so daytime highs, New Hampshire is expected to warm whether or not we act to reduce greenhouse gas emissions. However, the magnitude of warming depends on which concentration pathway we follow. And I think the temperature data or output here really kind of makes the case for the importance of trying to mitigate greenhouse gases now. So compared to the simulated 1980 to 2009 mean, increases of about 2 degrees Fahrenheit by 2040 are projected under both atmospheric greenhouse gas concentrations. But this pattern then diverges after 2040. So by the end of the century, under the higher concentration pathway, we have warming of about 9 degrees Fahrenheit compared to 5 degrees Fahrenheit for the lower scenario. So there's about a 4 degree Fahrenheit difference in average temperatures at the summer by the end of the century, depending on greenhouse gas emissions. And then in summer, daytime temperatures are projected to warm slightly more than at night. And with that, the occurrence of hot extremes are expected to increase. And so, for example, if we look at projected increases in the hottest day and night, they're expected to range or increase anywhere from 5 degrees Fahrenheit under lower emission or lower concentrations, and as much as 12 degrees Fahrenheit for higher. And kind of the big concern here is the frequency in days above 90, which are projected for the end of the century to be about double that under the high emission scenario compared to the low. All right, so we can cut our risk in half for this particular variable under the lower atmospheric greenhouse gas concentration scenario. And of course, then in winter, winter season is projected to warm faster than all other seasons, with winter minimum temperatures expected to warm the most, and this is consistent with what we've seen in the past. And so again, for the near term, winter minimums for both pathways show about a 3 degree Fahrenheit of warming over the next couple of decades. But by the mid-century, nighttime lows, we start to see a divergence with about 5 degrees Fahrenheit of warming for lower emissions and about 7 for high. And then, of course, by the end of the century, we're looking at a range of 7 for lower emissions to a warming of over 11 degrees Fahrenheit in winter minimum temperatures by the end of the century. And so, along with winter temperatures, these milder and shorter cold season overall gives a projected 19 to 35% decrease in heating degree days, indicated again a continued reduction in indoor heating needs that may or may not be offset by cooling needs during the summer. Like I said, happy stuff for a morning here. So we're not depressed yet. All right, one last little bit here, and this is precipitation. So again, like temperature, precipitation is expected to increase. But relative to the modeled historical past, so 1980 to 2009, precipitation is projected to increase by about 2 inches by mid-century, and not much more than that by the end of the century under both pathways, concentration pathways. But again, these increases, though, are due to the frequency and intensity of daily and multi-day precipitation events. So it's really the heaviest of rain events that are driving this increase. And so seasonally, increases in precipitation are projected for winter and spring, but of course the big question is how much of that is going to fall as snow versus rain. And so as winter temperatures increase, the proportion to stronger storms and more extreme hot temperatures, which threatens the health and well-being of New Hampshire residents. And then on top of that, rural northern New England residents who are already stressed by isolation and declining economic opportunities are particularly vulnerable to the changes in weather associated with a warmer climate, which has already had negative consequences on our northern forest ecosystems, impacting valuable rural industries and increasing our exposure to vector-borne diseases. And then the Northeast region as a whole is particularly at risk because much of our infrastructure, it wasn't designed even for today's precipitation or temperature extremes, let alone the ones that are projected in the future for future climate conditions. And our systems, a lot of our systems are nearing the end of their utility period. So continued global warming will exacerbate existing vulnerabilities, leading to increased risks of flooding and extreme heat, which threatens critical utilities and transportation infrastructure across the state as well as the region. But, at the end of the day, things are going to change, but we still have a choice because the amount of change to which we need to adapt will be less for a lower emissions, renewable energy efficient future. So there is time to lessen our risk, reduce our vulnerability, and make a difference as we move on through the next several decades. All right, so that information, that and a lot more will be available in the New Hampshire DES-funded state climate assessment, which is due out. I just got official word the other day. It's due out in a few weeks. But in the meantime, there's a bunch of equally cheery references for you to review for more information on state and regional climate and environmental change. And so I'd be happy to answer any questions you might have.
Plenty of time for questions.
Yes. Thank you.
So what's the good news?
There's still time.
Good.
That is the good news. That's the moral of the story.
Electric cars.
Yes. And and the thing is too, we do have the technology. There are technologies out there to mitigate. And statewide, there's a lot of work going on adaptation, but the problem with just focusing on adaptation is that if you don't mitigate, your adaptation isn't going to be enough. But we do have the technology, we just need kind of the socio-political will to implement it all. But, and then we'll...
Thank you very much for terrifying talk.
I know, I hope everyone had their coffee.
Yeah, so you mentioned the drier summers. Mm-hmm. Have you looked at the degree to which the drier summers make us more vulnerable to the rampant wildfires like we've seen spreading to more and more states across the West?
We have a little call-out box in the report on that. There is not a lot of work on Northeast forest fires because again they're rare. But yeah, as we get drier, have more of these, we call them flash droughts, these rapid onset droughts that can happen during the warm season when everything, trees are soaking up water, the temperature's getting high, people are using water, but then the rain. We just have a dry weather pattern and boom, we're there. That will increase our risk for forest fires. So there is.
Yeah, I'm wondering about geoengineering and the concept of sulfur aerosols in the high atmosphere, and what your opinion of that is, and whether we'll be forced to do something like that because of inaction.
Oh, I hope not. I mean, we have far better options than messing with things even more. I don't know. We've already put stuff in that has done things, and putting more stuff in to combat that, I think we just have much better options than going. We should really focus our energy and conversations on the options we have to mitigate greenhouse gas emissions and potentially store carbon as opposed to, just trying to cover it up. That's my opinion. That's just personal opinion. Personal opinion there. Yeah.
I was confused by the models that you said you were using for your data.
Mm-hmm.
I'm wondering if they were developed in the last 2 or 3 years and whether they take into account melting of the Arctic ice cap and the warming of the ocean.
Yeah, they do.
Secondly, is there a report about climate adaptation for New England?
Yeah, those were the same models that were.
Repeat the question.
Oh, repeat the question. So he was asking about the models and whether they take into account the rapid warming of the Antarctic ice sheet and ocean warming as well. Those, the models that we ran were from the last IPCC report, and that was the same model runs that were fed into the 2017 National Climate Assessment Climate Science Special Report. So those are the full coupled comparison models that were used in those larger global studies. So they are a few years old. Just as we finished all of this, the IPCC came out with the 6th report, so that's the new generation of those models. So when we redo this again in another 5 years, we'll incorporate those later models. So yeah, they are a few years older from the last set of reports, but they are the same ones that everyone else uses.
Can you cite us to any report about climate adaptation in New England?
Yes, the National Climate Assessments, the top reference right there, the National Climate Assessments 2018 Northeast chapter of the climate adaptation and impacts. So that was volume 2 of the climate assessment. I would refer you to that for more of the information. Great question. Go to the back.
Is it fair for me to ask, when I talk to my audience in my late group, right? Is it fair for me to ask you what geographic area weather will we look like in 2050 if we don't do anything? In other words, will we have the weather of Raleigh, North Carolina? Will we have the weather of Philadelphia or Camden, New Jersey? Or can I ask you that, or is that just too blunt a question to try with?
You can ask, but I will say, and I know where those are coming from. So it was in the 2000s, the national climate assessments were putting out comparisons of like North Carolina is moving north and we're going to be like New Jersey, or I've seen those before, and those are kind of a blunt, not entirely apples and oranges comparison of what's going to happen to our seasons. And so as time has gone on, we kind of cringe at that kind of comparison. But anecdotally, I went to graduate school in the Mid-Atlantic, and I got to say summers are feeling a lot more like Philly than New Hampshire that I recall. So there is kind of something to be said about those. But overall, warmer, wetter, but we're still New England. We're not going to be, the Carolinas. Two different kind of places, different dynamics, different weather systems, so they're not easily comparable. Yeah, I haven't gone right yet, so.
I don't know if you have recommendations or anything, but do you feel like there's things that New Hampshireites or New Hampshire legislation or residents can do to impact lower climate scenarios, or is it solely sort of a federal effort or even international effort to achieve lower emissions scenarios?
State level can do a lot of work. If we look at some of the programs that our neighboring states are doing to improve energy efficiencies in our grid system, also invest in renewable energy sources, there's a lot of that work going on at the state level. Even some local communities can join in, and of course individually you can choose a lower emission options for certain things. So there's definitely things that we can do at the state level. We don't have to rely on those other folks to run our lives. So, yes.
Thank you, Mary. Lots of things to make a person nervous here. Having shoreline property, the freezing and thawing in the winter makes me really nervous because that really causes a lot of damage to the shoreline and the infrastructure and everything associated with that. So you mentioned in the past 120 years we've already seen this shortening of about 8 to 11 days in the winter ice and off season. What do you project for the future on that?
Continued, kind of early onset of ice out. The difficult thing, and this is hard to model because it happens on such smaller scales, But I know the Department of Transportation is looking at a lot of this stuff, as well as other infrastructure projects where, these intra-seasonal freeze-thaw cycles that are going to increase as winters warm. So at night, as all the nighttime temperatures are shifting up, you're going to get closer to that 32 mark and go up and down throughout the day. So we're just going to have more small-scale freeze-thaw cycles within the season that also can be damaging to infrastructure, both, on water and near water.
You present data that shows more change from 1971 to now than you saw from 1901 to 1971, which suggests that things are changing faster.
Yeah.
So that would mean in the next 10 years, we'll see more change than we've seen in the last 10 years.
Possibly.
And the other question is, what happens in 2021 when the models end? Do we just sort of reset back to the climate of the previous century, or does it just go on?
Well, the reason we don't go beyond that is because that's when you get too much uncertainty with the projections, because we're just too far out. And so that's kind of where things are kept. Now, there are sea level models that go out for the next 500 years. But just what we tend to report on and what we're most confident about still is kind of the near term, 30, 50 years worth of change. And then we do go up. But as things improve and we further and further, when I'm ready to retire, we'll be projecting out probably to 21.